What's up, everybody? It's Sammy. Today I want to walk through uh, like a project I've been working on. It's a playlist generator. Um, I kind of had an idea from a project a while ago, and I just want to walk through it. Let's go to my project notes so I can give an overview. Let me make this window floating here. So as you can see, I'm using Linux right now. I'm using Linux for a while now as like a daily driver. This is a distro that's based off of Arch Linux. It's called Endeavor OS, and I can make another video about that, about Endeavor OS if you want me to. Just let me know. But I'm trying to resize this window here. Let's see. All right, sorry. I need to resize this here. There we go. Okay. That looks good. Wait. There we go. Okay. Okay, so let's go to the project. Name of the project is called Jukebox. So I wanted to make this project because I was interested in audio analysis, and I wanted to kind of create something that mimics like playlist generation, like streaming services, kind of like Spotify or Apple. You know, when you click onto Apple or you go on to Spotify and you click on a song and you click on Start Radio, it generates like a whole playlist, based off your favorite songs and your listening history and kind of like what you like, and it helps, and it finds, and they have like a recommendation engine underneath. And I think Spotify has machine learning algorithms underneath the hood when it comes to finding similar songs. Kind of like I think it's open source too. It's kind of like a K nearest neighbors type of thing. From my project's sake, I wanted to do something that's kind of like on a smaller scale, because I wanted to understand how audio analysis is done, and the math underneath, and I thought it would just be interesting. So, it's a project I'm working on in C++. It's called Jukebox. The whole idea is to first have a song as a seed, and then when somebody uploads a song or like to the application, then my algorithm will run its course, find similar songs, and then rank them, and then create a playlist. So it's a pretty small toy project for now. I might scale it once I have like an MVP, but I think it was a cool idea. The whole thing is just creating a playlist generator. Like, that's pretty much it. Nothing. I'm not working on a streaming site or a streaming app or anything like that. It's just I just want to learn audio analysis, how to create an engine that can match similar songs based off a seed song or a starting song. So this is the overview I have. This is just to-dos I have to do. So this is just an overview. So defining how to represent songs and their attributes. So, and I'll walk through the code too. So I'm basically using a SQLite right now. SQLite is like super versatile, and I love that it's just a single file and it's very simple, easy to set up. So, so that's what I'm doing there. And then this is kind of like how I'm going to handle files. So once I show you later, I do have a couple songs, like a whole playlist of songs from a bunch of different genres that I mashed up together into one directory. So that way I can perform like conversion, things like that. So the reason why I'm making this project is because I was inspired by this dude who made a Shazam, who implemented Shazam, like the algorithm for Shazam. So if you've ever heard of Shazam, you can go on your phone and click on record. It listens to a song, and then it finds the fingerprints of a stored song in a database to match that song that was recorded. So really cool. I'm sure you've heard of Shazam before. I use it a lot. I love it. And as a music head, like I really love it. I really love Shazam. It's amazing. But this person made a implementation of the algorithm through research, and I thought it was a really cool idea. They made a whole YouTube video as well and explained the algorithm in an easy to follow way. It was super amazing. This person's super talented. If you never heard of him, his name is, let me put this into floating. So I have an ultra wide monitor, so that's why I have to make the windows floating. So this person's name is Chigozirim. Sorry if I mispronounced your name. It's a cool name. It's fire. So, okay. So he made a implementation of the Shazam algorithm. And, you know, in this video, he mentioned a couple of resources that he looked at. I kind of looked at those, but for my case, it doesn't really relate to the Shazam algorithm because it relies on like fingerprinting songs. I'm kind of doing something similar to that, and I'll show you later how that's going to go. But this person made like a copy of the Shazam algorithm, and it's super cool. He has a demo video too, so you upload the song on Spotify, then based on what the songs that's stored in the database, it retrieves a fingerprint of that song, so that way it can then it creates like a score, ranks the songs by match, and the song that matches the most is going to be the first one that's ranked. And so this is really cool. He made it in Golang. FFmpeg, super popular library for multimedia processing. That's what I'm going to use for my application. And it was super cool, and I was inspired by this idea because I was just really interested, like how can songs be represented, you know, without using like machine learning or anything like that. I wanted to learn like how can we find relation between audio files? Like how does that happen? Like, how can we visualize? How can we make a score, a ranking of audio based on a seed audio or like a one song? It's kind of like Euclidean distance or like cosine similarity, and that's something that I have to learn and do some research on because you know, I don't know much about that. But this whole project is for me is just a learning, journey. And this person did that as well. Like they wanted to learn. They made a video. I implore you to check it out. It's on YouTube, and it's under the same name, his name too. And it's a really, really cool video, and it really inspired me. Like, you don't have to recreate the wheel, or it's okay to recreate the wheel sometimes because it's for learning's sake. You know, you can't always come up with an idea that's groundbreaking or innovative. For me personally, I want to just become a better engineer, a better developer. Get better at C++ as well as use tools I've never used before. So yeah, this is a cool project. Definitely, this is the one that inspired me. And then so I'm gonna go through. Let's see. Okay, so I'm gonna go through a couple resources that I read. So what I'm going to be implementing for my project is something called a Mel spectrogram. And to try to break it down, it's basically a way to visualize music or visualize audio files in a way that it's a function of frequency. So yeah, it's a function of frequency. And it involves a math-based idea called fast Fourier transform. To be honest, I'm not a genius at all, but after doing a little bit of research, I found this nice little picture that will kind of explain. So you're given input signal. You're given this input signal. It's just in waveform, so audio files. And what I'm doing is first converting every audio file that I collect into waveform, because waveform is a lossless format. It's you usually have the best quality with waveform, and I think that helps with finding similar songs, because because it's the most, it's the least amount of compression when it comes to audio formats. And so I'm converting everything to wave, place it into a database, and then what I'm doing here is a fast Fourier transform. And what it's basically doing is it's making window segments of the song. It's creating windowed segments of the audio file and then computing a formula which will then be used to create a spectrogram to visualize the audio. So let's say like for example, let's say that there's a song that's like fast beat, has fast drums, and it's very bright. Then the spectrogram or the MEL spectrogram is going to show brighter colors than like a slower song, because the whole idea of performing the Fourier transform is that it takes the audio and creates a spectrogram that makes it so like it's a function of frequency, because before that its intensity is a function of time. But since we want to focus on for the sake of focusing on the audio itself, we want a function of frequency. And so that's probably not the best way to explain it, but I found a few resources below here that help me understand it. The first one I found was this neural network one, and it kind of related to what I was looking for. So this is like a CNN, and it was used to create a MEL spectrogram conversion. So this is what I'm doing here. So I have a song, and then I want to query that song, turn it into a MEL spectrogram, and then I guess skip the CNN stuff for now, and then create a playlist and use similarity metrics to make a playlist. So the MEL spectrogram I saw is very popular to use because I think it's supposed to be like great. It's a time frequency representation of sound. So the important aspect of it is that it's a logarithmic scale for frequencies. So how we perceive audio and sound, if you just take that, if it's not logarithmic, if it's not on a logarithmic scale, our perceived sounds, our ears are tuned differently. Wait, sorry, my computer slept for some reason. Just had to change where the charger cable is ported, but whatever. Okay, so what we were saying, so like how we perceive sound is a little scaled than like reality, because when you listen to a song, a lot of the times the higher frequencies that we are more pronounced and enunciated to our ears than lower frequencies. So like for bass, for kick drums, for the lower frequencies, we tend to, like if everything was just normalized, we tend to overcompensate for our hearing towards lower frequencies, because higher frequencies or mid frequencies, our ears can listen to that more clearly. So for the sake of the logarithmic scale solves this for frequencies by reducing dimensionality, and it represents how we perceive audio closer. It's pretty cool. I'm not sure like how it really works, but it's cool. It's something. It's a real thing, So like for example, this is a spectrogram of a song by Joey Badass, and see as like the frequencies here, these represent the frequencies of the sounds, and it shows where in the frequency range, like where are the brightest parts of the song. So, you see here, this is a pretty empty spot in the song. That means the song didn't have as much energy. So it's like representing song in the form of energy, and a way to visualize that with colors and brightness. So it's pretty cool. This blog shows how to use a CNN. I'm not going to use a CNN. I probably will later on, once I am happy with like what I have. So yeah, it's a pretty cool idea. So you're making a logarithmic scale to you're making like a logarithmic scale of the audio, so that way it shows like the real, so that way it kind of forms, visualizes the song in a way that helps us, how do I want to say it, you basically want to make something that's like as close as how we hear music as possible. You know what I'm saying? Like, if that makes sense. But yeah, so that's one resource I used. And then there's another one. I wanted to understand the Mel spectrogram too. And this is a pretty cool blog post about that. So, oops, what's that? I don't know what that is. Okay, so what they're showing here is a signal. So the audio signal is amplitude by time. Amplitude, I think, that has something to do with volume. I'm not sure what amplitude is. I think I know it's volume. Yeah, I think it's volume or something like that. But as you can see, the audio is a function of time here. So the y-axis is time here, and then it explains the Fourier transform. And the whole idea is that, an audio signal is made up of waves. It's made up of waves, and what you want to do with these waves is you want to, instead of the audio signal being a function of time, you want to make it a function of frequency. So that way, this is going to help with finding similar songs, because songs are just a whole. It's like imagine grass, like imagine a lawn. Each song has a unique lawn. The grass can be long, very long on one song. There can be hella weeds on another song. There can be totally brown grass, or it could be dirt on one song. If there's nothing going on with the song and it's not that great, it could just be straight up dirt. And people love dirt. So there's some people that love dirt. If you want to listen to a song that was just made up of dirt, people like that. There's dirt songs I like too. But, the whole idea is that each song has like a unique character to it. And this is what the Fourier transform is helping us with. It's helping us convert the audio signals and formulate the audio signals in a way that you can represent the song in the form of frequency. Because when we listen to songs, it's frequency. You're listening to a range of frequencies. Some song can use up a frequency, use up most of a certain frequency range than another song. Another song can use more low frequencies, things like that. When you listen to old records, like if you listen to old jazz like Miles Davis, there's not a crazy 808 bass. It would be crazy if there was an 808 bass while Miles Davis is playing his music, right? That would be crazy. But it's gonna be very different from like a trap song, from like a Young Thug song, which uses 808 kicks heavily. So so there's a unique character. You're creating a unique character for songs. And this guy, he explained the fast Fourier transform and shows how it can be converted to frequency here. And then to create the spectrogram is like the bread and butter of my engine, like how it's going to find similar songs, because this is a whole like visual way to represent a song. And so what this is going to do is that it's going to take windows of an audio sample, and it's going to perform this FFT. And when I was studying like the Shazam dude, like the guy who made the Shazam here, he used the same idea as, performing the FFT on windowed segments, and then using a sliding window algorithm, which is something that I'm doing research on too. He did a sliding window algorithm to compute these windowed segments, and so when he's taking these, when he's doing the analysis, taking window segments and then placing them into like formularized, that's not a word, but you know what I'm saying, it's creating an output of the wave signal to prepare it for the spectrogram. And there's all this metadata like sample rates, window sizes, and channels that is important information for this whole process to happen. So as you can see, like this is a spectrogram. As you can see, frequency, which is hertz, and then time. So this is the result here. And it's really cool how like audio can be visualized, because it's something you don't really, because you know it's cool like when one thing is made for one like sense, which is ears, and feeling, because you know you can feel music too. It's cool to visualize it because it's like another whole dimension, you know. It's like the Matrix, sort of. But yeah, this is the scale here. As you can see, the logarithmic scale, it helps to dimensionalize the audio to a way that's closer to how we listen to music, which is important when finding similar songs, because you want to, the whole idea is creating the Mel spectrograms to scale audio as close as possible to how humans perceive the audio, you know, because our ears are different from like how digital audio signals are made, you know, because we have ears, and there's a certain amount of frequencies that we enunciate, and so we have to perform this logarithmic scale and create the spectrogram. So it's cool, you know, it's pretty cool. And I can go into details later on once I start implementing the code. You know, this is going to be like a little video series. I'm not sure how long it's going to be. It's going to take probably however long it's going to take me to make this project. So yeah, this is a cool little resource here. And then in order to work with audio files, I am using FFmpeg. FFmpeg is like a super popular multimedia engine tool. It's amazing. It's like a lot of video editors are pretty much wrappers around FFmpeg. Like FFmpeg is like the holy grail of multimedia processing. There's a project I made that's like a YouTube clone project. I use FFmpeg, but I'm definitely going to use the extent of it in this project. With my YouTube clone project, it was basically like just scaling videos to like 360p and then uploading it to the website. So it was really simple how I used it. But here I'm going to use FFmpeg, and let's go to the repo actually. So FFmpeg. So this is like the holy grail for multimedia processing. Like it has everything. You can convert audio files. It's an encoder, a decoder. I'm not really sure what that means, but yeah, it's what it is. But yeah, so this is FFmpeg. Again, like guys, I'm not a genius, you know. It's really just all about studying. Like how I never really knew about the metal spectrum at all until I, you know, sat down and spent a couple hours like trying to understand what it is, you know. So, you know, this whole project is just a learning experience, and you know, as engineers, like that's really how projects go. It's really, you want to learn about a tool, you find resources, figure it out, read about them. And so yeah, this is not the FFmpeg website. So let's go to the website. Here's the documentation. So yeah, so there's these, so they have command line tools, and then they have these libraries too that you can use within your own code. And I think all the functionality of FFmpeg is based on their libraries here. And so yeah, there's a lot. So like for example, there's encoders and decoders. So as you can see, there's a lot here. Like there's an extensive amount of information on how to use FFmpeg. So as you can see, these are decoders, coders. Not sure really what this is used for. Yeah, you see there's a lot. I think audio resampler is what I'm going to use. Yeah, see, so you can, more options than me. So like you can get the sampler rate. So it involves like extracting. You can extract information from audio files. And I'm using WAV files for my project because what is a WAV file? So it's a lossless format. It means you don't lose any information from the audio. So it's uncompressed, which is very important because you want to get you want to get the most information from an audio as possible. WAV is the best format for that because it's important that it's uncompressed. It has to be uncompressed, like MP3 audio, .FLAC audio, and like M4A audio. Those are formats that are compressed already. WAV makes it so like it's uncompressed in the first place, so that way you can get as much information from the song as possible. I'm not an expert on it, but that's just an easy way I can explain it from myself. So, okay, yeah. So I'm using FFmpeg, and let's go through like what I have so far. I don't have much, honestly. It's not that much. You see, that's my. So let's see, Tmux attach to Jukebox. The project is called Jukebox. So okay, so what I'm starting out with is, so these are all a bunch of playlists from YouTube. I'm using a tool called YouTube DLP, and it's a tool that's used to download videos from YouTube, from the CLI or the command line. And here, let me show you the repo really quick. It's pretty amazing tool. A lot of people use it. It's super popular in GitHub. It makes it super easy to download videos from YouTube, and it has a lot of functionality. So I used it for just like extracting audio from videos because I did not need the videos because it was not appropriate for my project. So it wasn't really, videos aren't useful for my case. So these are all of the playlists that I collected from YouTube. These are playlists that involve different genres of music. So soul, R&B, jazz, Afro beats, Latin trap, and classic rock too. So it's just like a whole plethora of music genres. And I wanted to get like a mix of genres because I think it'd be important to have a mix of genres to test out my engine. And so and then I downloaded the audio from YouTube in different formats because I wanted to also test my conversion function using FFmpeg to WAV files, because in my database I'm just going to have WAV files. It's just going to be WAV audio files. It won't be different. It won't be these other formats. The whole thing that I'm going to do is convert these audio files into WAV files. As you can see, I'm also downloading WAV files too. So I just want to take like a mix, because I want to make an engine that can be scalable, and I wanted to be able to convert all these different audio files to WAV file, and I want to do some testing on that too. So these are what I have downloaded so far. So let me show you the playlist actually. So these are the playlist videos that I got from YouTube. So 2020s R&B, so just modern R&B, 90s R&B, soul songs, funk, classic rock, jazz, reggaeton, Afro beats, Afro beats, and then just Latin stuff. Shout out Bad Bunny. Yeah, so There was a Bad Bunny playlist. I should have added that too. So these are all the playlists I'm going to download. So I've already downloaded one so far. So to like to extract the audio formats for the MP3 files, these are just like the list of the YouTube links here, and then I downloaded them to my project directory. Okay, so all right, so to go through the code so far, this is a long video. This is probably too long of a video, but whatever. So I'm using C++. Not the best at C++, but I solve LeetCode with C++, so it's kind of not, it's not new to me. But in making project is way different from LeetCode, so I'm having to learn as I go. So for my database, I chose to use SQLite because it was just very simple to use, and the guy who made the Shazam project, he used SQLite, and then I just thought I should learn SQLite and use that. So I'm using SQLite. I might someday use Postgres as well, add on to the project and make like an API for Postgres, something like that. But for now, I'm just using SQLite here, and then I'm using a SQLite library that's made for C++. It's called SQLite CPP, and it's just like an interface for SQLite in C++. And yeah, it's just like a wrapper around like the C API, because SQLite is made in C, so it's just like API with C underneath. So yeah, I'm using that, and then for the database, for the whole connection to the database, just a simple function. I use like a config file, made a DB client, so that way the DB can be ready for transactions or like executing queries. And so far for the SQLite database, I just have a new SQL client and then creating tables. So I haven't made the functionality to insert audio files or delete audio files or get by ID. I'm going to do that later, but for now my focus is to handle the conversion of audio files right now using FFmpeg, converting audio files, the raw audio files that are within this, where is it? Yeah, so I have this folder called test data, audio source. This is all of the music that I downloaded from YouTube placed into this folder. And what my goal is to do is, I'll make a later video on how I did this later on, once I had like the code complete. I have a config file that lists the directories of where the audio is stored, so that will be this audio source directory. And then what I'm going to do is I'm going to use FFmpeg to scan that directory, convert all those audio files into WAV format, or let's see, we want to scan the directory and then add entries to the database. And then these files, these unconverted files, so they could be MP3, they could be whatever format besides WAV, and I'm going to create entries within the database, so like kind of like making insert queries for the database, and then label these as new. And then I'm going to use FFmpeg, and I'm going to code a function that scans the directories, converts them to WAV, and then saves them to a processed audio directory, which is this here. See, that's empty, so I don't have the functionality yet. And then after that, I'm going to update the database record with that process file path, and then whatever metadata as well. So this is just a high-level overview. There's certainly like small details that I'm missing for sure. And then bang, then I create this Mel spectrogram calculation, do all that, and then at the end, it's a playlist generation algorithm. It's crazy, right? So that's what's going to be in the end. Again, I have to learn how to implement this MEL spectrogram. I'm gonna try not to use AI and like ChatGPT it, but I might if it takes a long time. But yeah, this is just all for learning purposes. Maybe it might turn into an actual application that people can use sometime. I don't know. That'd be cool. But yeah, so that's it for the video. If you guys have any comments or like anything to suggest, recommend, feel free to let me know. All right, peace. Thanks.